So another application of circular motion, Newton's second law applied to circular motion, is that this famous loop-to-loop problem. Supposing that there is no any friction between the object and the track, and we have this such a track that the track goes like at this point a circle, then it continues in this direction. So when you just release an object, it comes just enter this circular track, and supposing that it is making to the top, obviously with some speed, okay, and continuous motion without losing the contact from the track, and continuous motion in this direction, okay. So we're just curious about what must be the minimum speed of the object right at the top of the track. This is top point, this is bottom, this is top, this is bottom, okay. This is bottom, and this is just top. Or let me just put this object right over here at the top. So what is this minimum speed right at the top, so that the object just makes this full circular motion without losing the contact right at the top? Okay, so again we're applying obviously Newton's second law, and supposing that this is the radius of the track, okay. So let's make this radius capital R, and we have to show all the forces acting on the object, and also the forces between, well, anyway, acting on the forces acting on the object at the time. So obviously there is this gravity of the object, supposing that object has mass m. And by the way, this this is a famous amusement activity in amusement parks, like roller coaster. You just get into this roller coaster, the car, and just go in this circular track. You become upside down at this point, so you're making fun of the motion if you're not scared. Okay, so and also we have this normal force between the car or the object and the rod, but this normal force is acting on, when you think it's acting on the object, also it is also must be going downward direction. It's a normal force, and this is a very important point, that if you just drove this normal force in the upward, well, this upward is going to be the normal force acting on the rod, not the object. But if you, since we are thinking free body diagram for that particular object right at this point, we need to show this normal force acting in this direction, because normal force is always from the roadside toward in a direction which is perpendicular to the point wherever you are on the road. And for example, at this point, the normal force is in this direction. Okay, on the, of course, on the track, on the object, and at this point, normal force is in this direction. Okay, normal force acting on the road, of course, is going to be downward direction, sorry, in the reverse direction, but this normal force we are thinking on the subject, and the subject is our object, so that's why we should take the normal force in the downward direction. Okay, right over here the normal force is just in this direction. Okay, I hope you got the point. So all right, and are there any other forces, supposing that there is no friction in the road? So these are the only forces, right? And right at this point, the object has some speed. Well, of course, this speed is changing. It comes over here with a high speed, but as the object is climbing toward the top point, its speed is going to decrease. Well, right at the top, it's going to take the speed is going to take a minimum value. But right at the top, if the speed takes very low value, there is this danger that the object lose the contact to the road, that means the object will just fall down, okay, in a free fall. So we don't want this to happen. If you insist that there is still some normal force, or there is still some contact between the object and the rod, that means the normal force is going to be not zero, okay? All right, so anyway, let's get to the point. And right at this point, all forces acting on the object must be equal to just m times a, but since this is a circular motion, a is just right at the top, is v squared over r, all right? But what about these forces? Well, you can take, since also the direction of the acceleration is also downward, right? Right at this point, the direction of the acceleration is also downward, and you can always take all these downward directions as positive. So in that case, you get the n plus mg, which are the forces, and on the right hand side you have mv squared over r. So if you solve this for the normal force, what you get is mv squared over, sorry, let's write this as mg v squared over r times g, right, minus 1. If you solve for n, this equation, this is what you get. Okay, let me put this rg. So we want that, as I said, the object just go through this point without losing the contact. That means we just want n to be larger than 0, or maybe a minimum equal to 0. So because from this point on, from top point on, again the object starts increasing its speed, so there is not going to be any danger when it's increasing speed. But the condition that there is no 0, or at most it's 0 value for the contact right at this point, is that this parenthesis expression v squared over rg minus 1 must be larger than or equal to 0. That gives the condition that v squared must be greater, or at least at minimum equal to the value r times g. That means v is just equal to or larger than this value rg, and r is just the radius of the track, and g is just a gravitational constant, which is 9.81 can be taken as. Okay, so this is the minimum speed that the object goes through this top point without losing the contact from the track.